Best. All right. Hi, everyone. Welcome back to the stream. So in this stream, we are building a rendering engine in Haskell using Vulkan. Um, so yeah, we'll be going through that whole process live on stream. So last time we got round to presenting a triangle on the screen. So we managed to get that working. But we found that when we went to resize the window, uh, the swap chain would be out of date, throw an exception, we wouldn't handle it, the program would crash. So there are some resources that we have that are dependent on the swap chain. And when the swap chain changes size, we need to recognize that the swap chain has changed size. We need to recreate any resources that are dependent on the swap chain, um, and then get back to rendering. So, just a reminder, you can follow the project at github.com/sambnt/RORT. And here you can follow the commits live. And I also upload the streams to youtube.com/@SamBennett_TV. And here you can watch the past streams, and I'll upload this one when we're done today. So what we're going to be looking at today is handling the swap chain out of date exception and recreating any swap chain dependent resources when that occurs. So we've grouped our swap chain dependent resources into this function called per swap chain. So per swap chain takes some information about our render pass, and then it will return us some resources that we can use to render to later. But it's a little bit unclear that's happening. It's a little bit difficult to infer that that's what we're doing from the types here. Like, what does this mean? What does this mean? And what do these return types mean? And why do we have this like double list of like a vector of lists? It's a little bit confusing. So I think while that piece of code is still fresh in our minds, we should create some better types for this function. So we know that when it comes to Vulkan, we just open up a whiteboard. We had a look at this last session. When it comes to Vulkan, draws are made up of multiple render passes. So let's get rid of this. You might have a frame. So with a rendering engine, we're drawing one frame at a time. So you might have some frame, and it might be made up of multiple render passes. So we might have one render pass for the opaque objects in the scene. We might have another render pass for the transparent objects in the scene. Now those render passes can be made up of multiple subpasses. And so on. You can have as many subpasses as you want. So the subpass will like look after like a particular component of that render pass. So what we're looking to describe back over here in this function, per swap chain, is we want to describe our render passes, which are composed of subpasses. So we'll describe our subpasses, we'll collect them into a render pass, And then we'll pass a list of these render passes into this function here. This function will then create the resources that we need and give them back to us. So let's start with the subpass info, because that's kind of the smallest level, lowest level. So subpass is made up of shader stages. So in our simple example, we've got a vertex shader and a fragment shader. The vertex shader just draws the points on the screen, and then the fragment shader is going to fill in that triangle that we see. So the vertex shader is outputting these 3 vertices of the triangle, and the fragment shader is creating this nice like color gradation in the surface created. So we need to specify those shader stages, and that corresponds to this argument here. So we can actually just copy paste that. All right. We also need to specify our pipeline layout. So we're not actually using this at the moment, but we will be soon. So the pipeline layout refers to all of the descriptor sets that we use in the shader. Hi, welcome back. Oh gosh, you didn't get food poisoning, did you? Yes, another part of a subpass is the descriptors that we use during the shader. So that might be like the position of the object or the matrice that represents the position of an object. So we can change the position of the object over time. We don't have any of that at the moment. So but we still need to specify a pipeline layout. It just needs to be empty. Ah, rough. Lactose intolerance sucks. And I feel like people in Australia don't care that much. Okay. Excuse me, I'm just going to refer to my notes. Hang on a sec. Yeah. Oh no. There's some construction happening here, so I hope it doesn't disturb the stream too much. Hang on, I'm going to turn on my mic and see if I can hear it. Oh, no, it sounds okay. That's a real blessing. All right. Great. Okay, so that's our subpass. Then let's talk about our render pass. So render pass is just made up of subpasses. Um, this is just our first go at these structures. They'll change over time, but we're not using much of the flexibility right now. So a render pass is just made up of subpasses. So we'll just pass in a list of those subpass descriptions. Then this is kind of like our input. This is describing, and then This is going to be our output. These are sort of our resources that actually output. So for each subpass, we're going to want the pipeline. So that's the pipeline that's created from these shader stages and this pipeline layout. Yeah, I think that's it for now. And then for the render pass, we need the render pass, the Vulkan render pass, and then subpasses. And again, it's just going to be a list of subpasses. Now, the data that we actually output from this per swap chain function is frame data. So for each swap chain image, we're going to output one of these like frame, like this imaginary structure, this frame data structure. So for each swap chain image, what we're going to do is we create a render pass, we create a frame buffer that uses a swap chain image, and then we're going to output this like frame data structure full of stuff. And that's why we're going to get a list of them. And when we go to render, we're going to choose one of those based on the available images, and then use that to render. So this is going to be pretty simple. So we're just going to, for each swap chain image, we're going to have a frame buffer and we're going to have a render pass. And that render pass is referring to this render pass here. So we're going to change this function. It's going to take in a list of render pass infos because we can have multiple render passes, and those render passes are going to be made up of multiple subpasses. And we're going to output a list of frame data rather than this complicated structure here. And thanks, man. It is coming along. What's Unifex? Okay. List of render pass info. We're going to output a list of frame data. Okay. Yeah, wow. I do remember you mentioning that actually. What are you using those bindings for? Are you hoping to bind to Vulkan, or is it something else entirely? Okay. So we're taking a list of render pass infos in, and we're going to return a list of frame datas. We've wrapped that in a resource because we're going to be allocating things, and this will let the user free it if they want to. So we are going to have to change this function though, because we assumed that we were only doing one render pass and one sub pass. So let's get around to doing that. And rather than naming this per swap chain, let's call it make frame data. Oh, sounds pretty hairy. Okay. So, like I said, we assumed there was only one render pass, but actually a list of them. Did you manage to find your lost package? Okay, so we'll create our render pass. There we go. You can see that we don't have any, the render pass info structure, it's just made up of the subpasses. It doesn't have any like any members here that we can use to configure things like the attachments and the subpasses. We'll get around to that later. So then, just gonna make sure this indentation's the same. So we've made the render pass. Then we're gonna create the pipeline create first. So for each of the pipelines in the render pass, or each of the subpasses in the render pass, we're going to create the pipeline for that subpass. So let's start with render pass info subpasses. Yeah, it's just the plate. We'll be adding the bangers and mash later. I just don't want to like, I think when people are watching something, they want to understand the motivation. So like adding all of this structure to something before there's any need to, I think is confusing. So just try and get around to adding the structure when we actually need it. You know, when our code starts breaking, it'll become obvious. It's like, oh, you've added multiple subpasses, but you didn't describe them here in your render pass. Code is broken. And then it's very easy to motivate a fix. So we need the subpass index as well as the subpass info. So we'll just assume what we'll do is we'll zip an infinite list with the subpasses. And what that'll do is like zip will we have a list of subpasses. So we got subpass 1, subpass 2, subpass 3. Or more accurately, like when we're talking about computer science, we have 0 index lists. So subpass 0, subpass 1, subpass 2. What we're going to do is we're going to zip that list with an infinite list of numbers. And what zip does, I'm going to reverse the order, is it takes the first element from this first list and like attaches it to the first element of the second list. And so what we get out is like 0 subpass 0, 1 subpass 1, 2 subpass 2. And then when we iterate over this list, we can get that subpass index and the subpass itself. And then we can do something with the subpass index and do something with the subpass. So that's what I'm doing here is I'm basically just giving each subpass an index that depends on their place in the list. And then we're going to basically just do what we did before. So we got this massive structure. Great. And we're going to get the pipeline shader stages out of the subpass info. Going to get the, that's the same thing. It's also this shader stages. This one's just the length. This one's the actual shader stages. And then keep going down. None of this will change. No multi-sampling. Yep. We're going to need to get the pipeline layout out of the subpass info. And the subpass index is going to come from the zip that we just made. Subpass index. Cool. So for each of the render pass infos, we're going to make a render pass. Done that, I'm going to create the pipeline create infos for each subpass. It's not going to be do. And then we need to actually create those pipelines. With VK graphics pipelines. No handle. Nice. I'm glad you're looking it up. I'm glad you're interested. See, you looked up basically zip in Elixir. It's cool. Okay. So we've got our pipelines. So what are we trying to return here? If we look at if we refer back to our types, we're trying to return this frame data. So we're going to return the frame buffer and a render pass. For each render pass, we're going to return the VK render pass, which we've already created. And we've got to return this list of subpasses. That's just made up of the pipeline. So we've got the pipelines. I think all we need to do then is we've got these pipelines. Let's just fmap subpass, or map subpass over them. But gonna have to do it twice. Oh, let's have a look at this type. Okay, what's the type of this? Okay, we got a resource vector of VK pipeline. Let's going to fmap so that we're working on the resource. We're going to change the vector to a list, and then we're going to fmap subpass over it. It's a little bit complicated, but what we're doing is the subpass is just made up of a single pipeline, and we're just going to iterate over the list and make the pipelines into subpasses. Okay. And from this, we're going to return a render pass, which is made up of the render pass and subpasses. Oh, and these are all resources. Great. So from this big thing, we've got our render passes. And now, so we're going to make our frame data, frame datas. So vector to list the VK image views. Like I said, for each swap chain image view, we're going to create a frame buffer. Rather, for each swap chain image view, for each render pass, we're going to create a frame buffer. And for each render pass, am I rolling I3? Yes, I'm rolling I3. No, I forget now, X monad, but it looks very similar to I3. X monad is like, which is very similar, but it's configured in Haskell, which is interesting. I don't really touch the configuration anymore. I need to make something pretty like yours, but I'm a little bit too used to the, yeah, no, it's great. I'm a little bit too used to being able to switch windows like this so easily. Okay, yeah, we're going to create a frame buffer for each render pass, for each swap chain image view. Going to get the render pass. We're going to attach the swap chain image. Attachments. I'm going to set the dimensions of the frame buffer. We can just copy this from down here. And let's get rid of this old code. Cool. So that's our frame buffer. And then we're just going to, because we need to return a list of the frame buffer in a tuple with the render pass, we're just going to do that. We're going to attach the frame buffer to the render pass. So the reason that we have to do this kind of strange syntax, like the alternative would be frame buffer render pass. Like that's what you'd think we'd have to do. But because this frame buffer and this render pass are not the raw types themselves, they're actually resources of those types. And resource is an instance of applicative, so we can use this applicative syntax to join the two things together. So let's make sure we get that indentation right. And great, so what are we getting back here? Have a look. We're getting a monad of a list of resources. Cool, so that's fmat. Let's have a look again. Cool, we've got a... I thought that's what we had before. What have I done? So... Oh, whoops. Yeah, that's a good alternative. Virtual desktops. We might be able to use the virtual desktops instead of the Xmonad Dex desktops. Alright, so we got a list of resource of frame buffer, and we're just going to join that into one big resource. We can do that with sequence. So if we have a list of resources, we can join them into a resource of lists. So we can kind of swap this around. I'll just show that here. So if we had like a list of resource A, then if we put sequence, if we use sequence on this, we get out a resource list of A. So that's what we're going to do here. That's going to give us a resource list of frame buffer render pass. You can see that. If we put a little underscore here, we get a resource of a list of frame buffer, whatever. And then we're going to fmap our frame data over that. So that way we've got this frame data here. We should just be able to return that. Let's have a look. Oh, no, we've got a list of resources frame data. So we just sequence again. We should have we should get a resource list of frame data. It's a little bit screwy and I didn't do that in the best way, but that'll work. All right, let's fix any errors we've got. 419. Have I ever done networking with Haskell? Not really. Like I did a side project with it and it was good, but nothing in production. So I kind of will reserve judgment. I mean, I've done like web service stuff, and I guess that doesn't really count as networking, but yeah, I like it. It's some pretty good libraries. All right, what's going on here? Cool. So we've got a list of these things, and we need to create a vector of some struct. So vector to list. Sorry, vector from list. And then you will fmap, okay, some struct. Cool. And per swap chain, it's not called that anymore, it's called make frame data. Call this frame datas. Okay. This is not how we specify subpass anymore. Let's see how we do that. Let subpass info equal undefined. Render pass info equal undefined. So our frame is made up of a single render pass. So we'll pass that in. Don't need these more. Yeah, I'm not really like teaching the fundamentals, I'm just kind of like using it. So I worry about it as a learning resource, but you know, if it's helpful, great. Really, it's kind of like just get things done. So all we're doing here is just rephrasing the arguments to this make frame data structure because we've changed the type signature. Um, so we're not going to change anything about our render pass at all. We're just changing how we specify it to our renderer. Cool, that's it for that. What's wrong there? Ah. Yeah, that'll do. Yeah, good. It's about teaching the vibe. All right, so we specified our subpass, specified that our render pass is made up of one of these subpasses, and then our frame is made up of one of these render passes. So now we've got some frame data. What we're going to do is we're going to get that image index. So we're going to acquire the next image from the swap chain. That's going to give us an image index. And then we're going to jump into the frame data's list at that image index. Thanks, man. So let's frame data equal and get our frame data and I'm going to grab the image index. Cool, you don't need this 4M anymore. Didn't need it in the first place, but anyway. So, render. Okay. Got our frame data. What's in a frame data? I've already forgotten. Okay, it's made up of our render passes. So, 4M frame render passes. So for each frame render pass in the frame data, we're going to get frame buffer and a render pass. We're not going to return anything, so we can use that. Cool. So we let the clear value, most of this isn't going to change. So clear value is the same. Think, just use the render pass. This is the frame buffer. Cool. We're going to change the indentation of all this. All right, give me a sec. Something I find a better solution for is indentation. All right. I need something to highlight like what level of indentation I'm at, especially when I'm working on a small screen. But all right, so for each render pass, we've got a frame buffer, we've got a render pass. Going to begin the render pass. Set our viewport and scissor. All right, we're gonna need to bind each pipeline. Let's not assume there's just one. So triangle subpass. So if we get out the subpasses, 4M subpasses in our render pass. Each subpass just has one element, the pipeline. Don't need that anymore. Yep, so for each subpass, we're going to bind a pipeline and then do a draw. And we'll make this draw configurable soon. Then, going to end the render pass, and then all of this stuff is going to be out. 4 levels of indentation. Cool. So, fix any errors we've got. So this is how it kind of works. We acquire the image, set up our synchronization stuff, get a command buffer, and then we're going to record everything to the same command buffer. So for each render pass, I'm going to record begin render pass, set up our viewport, then we're going to record for each subpass, we're going to record bind pipeline, do a draw. After all the subpasses are done, we're going to end the render pass. Then after all the render passes are done, we're going to end the command buffer. Then we'll submit it. Cool. Looks like got a redundant import. Get rid of that. So hopefully we haven't changed anything. It should just work as before. Great. So we're still crashing with the swap chain. That's okay, we'll fix that next. So all we've done here is made some better types to kind of represent what it is that we'll be dealing with mostly, which is render passes. We know that the render pass is made up of multiple subpasses, and we've just got ways of specifying that. Then we've got ways of creating the Vulkan resources for those things and returning them. And then we've got a way of taking one of these and rendering it. Cool. Is the end goal of this bad boy to have a real quick Vulkan API situation for Vulkan where you can run a lot of the functionality of the base Vulkan Haskell patches? Yes. So the end goal is to have, like a high-level way of describing render passes and like their attachments and blah, 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 so that we can experiment with different types of rendering. Like these frame breakdowns that I talked about. So these frame breakdowns, they talk about how a frame is rendered in these terms of like render passes. And so if I can translate that into, my code, then that'll be great. That's the goal. And then along the way, I mean, we're going to have to make like some sort of camera system and some sort of movement system. So it'll basically be a game. But our focus at the moment is on rendering. And once we have these little parameters, we can start working on things that are more complex, like, this sort of this kind of screen space reflections using a previous frame. That's like a lot more complicated, but we'll be able to describe that at a high level, which will keep things relatively simple. So that's the goal. Yeah, no, it's no big deal. All right, let's call this like better render types maybe. Create types for describing render passes and subpasses. And we'll start to share this. We'll like write more examples. So like this one's just a triangle one. We'll like move on to an example where we're using vertex buffers. And we'll start to share this code between the examples, and you can start to see the rendering engine kind of extricate itself. So the next problem is this whole swap chain out of date issue. So what's happening is when we go to present the image, even also when we acquire the image, same sort of thing, there's this opportunity for the result to tell us that the swap chain is out of date. And what we're doing is we're throwing an exception in those cases, whether it's out of date or suboptimal, and that's crashing the program. So what we want to do is we want to let that exception bubble, or one way to handle this is to let that exception bubble all the way up to the swap chain dependent data. So if we move this command pull out here, because that doesn't care about the swap chain, we can have something like handle, how about retry on swap chain out of date. And then we might pass in an initial swap chain, and then it'll provide us with a swap chain for the block. We'll put all of this, like our whole program, basically. We'll put the whole like rendering and swap chain dependent block in that swap chain code in that block. So then the exception will bubble up to here. Retry will handle the exception, recreate the swap chain, and then restart this block. So this might not be the best way to do it in the long term, but that's okay. We'll start with this for now. So I reckon we can create this code in the swap chain module. So retry on swap chain out of date. So given some initial swap chain, what are we going to do? So we've got this function called handle if, and it'll catch only certain types of exceptions. So if is swap chain out of date, we should have a, oh, we don't. Is, oh, no, okay. It's okay. So if the swap chain is out of date, let's just say we've got some user function. We're going to run the user function. If the swap chain is out of date, we've got a handler. And in that handler, it's going to get the exception as an argument, and we're going to ignore it. So this is our handler. And that handler is going to be like, create new swap chain. Oh, we can just do so with swap chain. It's going to need the context, so we'll pass that in as an argument. So this will be our new swap chain. It's going to need the number of frames in flight. Not sure how we're going to do that right now. It's going to need the frame buffer size. We can do that, get that from the context. So vk get frame buffer size from the context. How have you found the lack of mutability so far? Good. Great. Yeah. I mean, we're doing lots of mutable stuff here. Like all of this code is in IO basically. Like where in IO means that we've got side effects. And like one of things about Haskell is you want to try and write as much of your code purely without side effects and then leave the side effects kind of to the end. You want to be able to create descriptions for your program and then have like an executor run them. And we'll get there, but like at the moment we're just like just reading the file and we are creating the swap chain and all those things. They have a side effect, so they're not pure code. And basically all of this is not pure code. Where we're starting to see pure code, where we're starting to see this kind of description are in these render types. And we'll see that kind of form more over time. Um, but yeah, we're going to be using a lot of mutability too. Like later on, rather than like, I think what'll happen, rather than us kind of retrying when we get a swap chain out of date exception, we'll probably just have some like mutable variable. So you can have mutability in Haskell. We'll just have a mutable variable that like holds the swap chain and like it's a thread safe mutable variable. And we'll probably, because we might have multiple threads drawing at the same time that might need access to the swap chain. So we'll have to handle this kind of like, okay, multiple threads are trying to use the swap chain, but the swap chain just went out of date. We need to recreate it. So let's acquire the tvar and like that way no other threads can render anymore. And then we'll recreate the swap chain, put it in the thread, but we're not there yet. The lack of mutability is good. Um, but at the moment, I'm just ignoring it. It's in the back of my mind. So, it's too hard to create like a completely like beautiful description of the program that's pure, that then the renderer takes and creates, this program that runs and renders everything the way you want. Like, it's great and we will get there, but got to take iterative steps. It's just too much to do it all at once. Hmm. That sounds like a cool way to do it. That's good. Like using the same tool for everything can be very helpful. All right. So if the swap chain is out of date, get the frame buffer size. All right. One of the things that we have for the swap chain is we can pass in an old swap chain um, to help um, reuse resources. So we'll do that. We'll pass in the initial swap chain. And that way resources can be reclaimed from the initial swap chain. Well, thanks for the follow, by the way. Then, once we've made this new swap chain, we'll free the old one. So we'll free that initial swap chain. And then what we'll do is we'll call ourselves. So we'll retry the swap chain dependent computation. So retry. What we're going to do is call ourselves retry on swap chain out of date context. But the initial swap chain now is changed. It's now the new swap chain and recall users function. So what we're doing is like when we get that exception, we're handling it and we're recalling ourselves. That way we're going to be like constantly managing that swap chain. This is a very like straightforward way of doing it. I'm not sure this is a great idea, like especially putting like the basically an infinite it's basically an infinite loop in the handler. I'm not sure that's ideal, but that's okay. We'll keep that in mind. Thanks for the follow. That's awesome. she'll be right is definitely the way to go. Like the thing I'm worried about especially is like multi-threading. Like, okay, what if I have multiple threads trying to use the swap chain? And like that's just it's not the right question. That's a very speculative question. Like it's very possible that we'll have only one thread trying to use the swap chain and multiple threads will be like recording draws, but not using the swap chain. We'll just have one thread using the swap chain. So that's like a very likely scenario. So it's good not to care too much about speculation. All right. So we need to import this handler function. Okay. And we need to write a function that basically just so we're going to write a function that identifies if this exception is a swap chain out of date exception. Should import everything. That way we can use it with handle if. So it's only going to handle swap chain out of date exceptions. We'll import get frame buffer size. All right, number of frames in flight. So let's store the number of frames in flight when we create the swap chain. That is the dead simple way. And then when you create the swap chain, we're just gonna go ahead and store. At the moment there's no way to change it anyway, so it's always gonna be the same, like once it's created. Then we can just go ahead and get that from the initial swap chain. Great, it looks like it's compiling. Variable not in scope. Ah. Yeah, well, this is iterative software development. We're not saying it's good. We're saying we'll make it better, which is often an empty promise. But we will actually make it better. Because, I said it, it's been recorded now. All right, retry. Let's import that. Pass in the required arguments. Call this initial swap chain. If the Prime Minister can lie, then so can I. Okay, what have I done here? Lift IO, monet resource. Hmm. Oh, probably forgotten some. Yeah. Just have to embed our IO computations. So we're working in the resource monad, so any like just IO computations we need to embed in the resource monad, which is what I'm doing here. Blah, blah, blah. I kind of had already half done, so we don't have to do it everywhere. Oh, is that what I need to do? Okay. Ah, we have to pass the initial swap chain. This is wrong. Let's just undo some of that. Swap chain. So we're just fighting some compiler errors. Looks okay. Great. Okay, that's compiling. All right. So just to review the type signature of this, we pass in just the context, the initial swap chain. Then the user will pass in a function that expects a swap chain and then returns some sort of like computation. And then what we're going to do is if the swap chain's out of date, like if we get an exception, we're going to recreate the swap chain, free the initial swap chain, and then retry the user's computation with the new swap chain. So let's run that. Oh, and yay, so we can now resize the window and it's not crashing because we're catching that exception now. So that's great. But there is a small, just a minor issue here. So like if we take some resource creation like this, like creating the frame data, what's going to happen is the first time we go through is we're going to create this resource and then like the swap chain exception is going to hit and then we're going to create the resource again and not free the previous resource because we haven't like explicitly freed that resource and the scope of the monad resource computation has only expanded. It hasn't closed. Even though there was an exception, like we handled the exception. And so like that computation is like allowed to continue. And so the scope of the resource lifetime is only increasing. And so we're just going to keep creating these resources and never freeing them. And so I can demonstrate that. Um, let's choose one like render pass. And in this, we'll like put some little debug statements like creating render pass. And then, oh, destroying render pass. Yes, it's like a zombie. So, have a look. So we create the first render pass for this initial frame. Then we, initial like swap chain, we resize and look, we're creating again, resize again, we're creating again. So we've done that 5 times now. We've created 5 resources, but we've freed nothing. So only when we quit the window, that'll destroy all 5 in like reverse order. Which is like great, it is destroying it, but not when we want it to. So let's fix that. In this function, what we're going to do is we're going to run the user's computation. We're essentially going to limit the resource lifetime to 1 swap chain. So anything they create in this block will get destroyed in this block, which is something to keep in mind because there might be things that you want to persist between swap chains. It's like, well, don't put it in this block. Um, yeah, and that's one of the limitations of this approach. But we'll figure it out if we exactly run into it. So all we need to do is run resource T. And all this is going to do is just, this is the user's computation, and we're just going to run it. So just import that. And what that does is effectively just like limits the lifetime to that block. And the return, the types of this function are going to change. Yeah, it's like a one shot. Yeah. Which is, in our case, the intended, like kind of the behavior we want. So now we're creating the render pass, and then it's hard to see. Create the render pass, then when the window resizes, we destroy the old one, create the new one, and so on. And then at the end, when we destroy everything, we're only destroying one render pass, because there's only one render pass that's left. Cool. So let's commit that, because we've managed that swap chain issue now. Yeah, it might require a big structure rewrite, but thankfully we've only got one example. So like, um, the way that I've approached this problem before is having like a step-based renderer, which is I think what we'll move towards, where you just call like you like initialize this renderer, you call step, and it will render the next frame. And if there's like an exception, like if it says like swap chain out of date, essentially just abandon that frame. We recreate the swap chain, and then we let the user call step again, and it will use the updated swap chain. And the way that works is that we have like a mutable variable that's got the swap chain in it. And when we detect that exception, we update that mutable variable with the new swap chain. We abandon that step, and then the user is going to call step again, and then they're going to get a step with they're going to run the render reaction again with the new swap chain. Um, so we still will be handling an exception, but it's just a little bit more intuitive way. Um, yeah, but I'll keep that in the back of my mind. Okay. Oh yes, I'm gonna commit all this. Oh, except that we don't need that. Review this. Okay. Should we say here? Handle swap chain out of date / suboptimal exceptions. Cool. Yeah. Yeah, I like the idea of programming in games. Seems like a cool idea. But just difficult to implement, you know? And also, like, I really want to give multi-user dungeons a go. I, I heard about them, had friends like obsessed with them, but I've never actually tried one myself. Okay, I'm just going to take a quick break, and then when we get back, we'll take a look at the next thing. I think we'll move on to another example. We'll try and get a square rendering using vertex buffers. Maybe. I'll get back to you. All right. The idea of it would be a developer can add, play the game. Yeah, that would be cool. Yeah, okay. Be back soon. Okay, we're back. So we've rendered the triangle to the screen. We've managed the creation and recreation of the swap chain and the associated resources. And I think now what we'll try and do is create a different example, a new example, where we render a vertex to the screen or a square to the screen using vertex buffers and index buffers. So you can start getting into buffers. So to start off, I'll create a new file called buffer.hs. What happened there? It's not quite what I want. And we'll just copy all of the code from the triangle example. We'll rename the example. And we'll just reuse the same fragment shader, but we'll change the vertex shader. So what might that look like? We'll create new vertex buffers. Put that. Cool. Oh, well, we actually already got this here from my history. Yep, okay, so we'll create a new vertex buffer, vertex shader, and what that's going to do is it's going to take in vec2 of the position and a vec3 of the color, and just output that. So instead of specifying hard-coding the vertices in the shader like we did before, I'm going to feed them in via a vertex buffer. All right, and I'm going to go ahead and compile that to SPERB. Then we can just change this to vertex buffers, and we're on our way. Okay, what needs to change? None of the shader creation code needs to change here. We still don't have any descriptor sets or push constant ranges, so our pipeline layout isn't going to change. Command pool is not going to change. But we are going to need to create some buffers. So what I imagine this will look like is we'll create a buffer for staging. So we'll upload our vertices to that buffer, and then we'll transfer that buffer to another buffer that is device local. So it's like graphics card memory, and we'll keep the vertices there. So we'll create a buffer for staging, then transfer that buffer over to production, basically. That's so that the graphics card has the fastest access to that information. And it's a good exercise for us because it's something that we're going to want to do later. So let's specify the vertices and their size. Do that here. So it's got the vertice like screen space position, and then it's got a color. There you get the size of that. All we're doing is multiplying the size of the float by the number of vertices, or the number of items in this array. Every 5 floats is a vertex. Then we'll use some indices to draw that. So this is going to draw two triangles, one made up of vertex 2, 1, and 0, and the other triangle made up of 0, 3, and 2. Okay, so we're going to wrap a call to with buffer from Vulkan. So we'll use what we normally do with vk buffer, and then pass in the buffer create info, which we don't know what that looks like yet. But we are going to need to create this function. So with vk buffer, it's just going to wrap the raw call to Vulkan. Is that buffer create info? Yeah. We're going to return vk buffer. Just like everything else, going to use our resource helper. We'll provide it a call to create the vk buffer, create buffer. Let's have a look at the type signature for this function. Alright, create buffer. Oh, I've chosen the wrong one. Go to device, buffer create info, and then allocator. So device, create info, nothing. And with the buff, you can destroy the buffer. Device, buffer, nothing. Oh, we have to pass that argument to it. There we go. So what does the buffer create info look like? Okay, we've got this chain, we've got flags. Do we need any flags? No, we're not using any of those. Got the size of the buffer, what it's used for, sharing mode, and if it is sharing, any Q family indices. That will be sharing that buffer. So for the chain, we're just going to leave it as the empty chain. We're not using that. Not using any flags. The size is going to be the vertex buffer size plus the index buffer size. The usage, it's going to be both a vertex buffer, so we're going to give it the vertex buffer bit, and the index buffer bit, and also it's the source of a transfer, so transfer source bit, because we're going to transfer from this staging buffer to the device local buffer. Is this operator a binary AND? No, it's a binary OR. So the binary AND looks like this. This is the binary OR. So it is both a vertex buffer and an index buffer and a transfer buffer. But I'm using the word AND because of the English. It's bad. Now this buffer isn't going to be shared between any of the queues. It's going to be exclusive to one queue, so we can use sharing mode exclusive. And that means that these queue family indices will be ignored. Go ahead and import this. great. So we've made the buffer. This is our staging buffer. Let's call it that. Now, unfortunately, this doesn't allocate any memory. Don't be deceived by the size parameter. Tells you the size of the buffer, but not like the memory that's kind of bound to the buffer. So we're going to have to create that as well. Staging buffer memory. So we're going to have some function called with bk buffer memory. It's going to take some parameters and it's going to give us the staging buffer memory. And then we'll have to call Vulkan. Yeah, this is, yep, a lot like OpenGL, C++. All the same concepts. So this is a Vulkan call, so we can have a look. We can look that up. That is the wrong one. Device, buffer, device memory, and then offset. So device. Oh, I've gone ahead and frozen my computer. Give me a sec. How do I manage that? Oh yeah. Huh. Still not working. Hang on a sec. What is taking up resources? Okay, we're back. Okay, if we wanted to bind the buffer memory, we'd get our buffer. We'd get the staging buffer memory. Then we'd have an offset of 0 because there's no need for an offset. And that would work. That would bind our staging buffer memory to the staging buffer. Then we'd actually have a buffer that we can use. So we're going to need to write this with vk buffer memory function. This one's going to be a little bit more complicated, because we're going to have to do some work to figure out what kind of memory is appropriate for our buffer. Hey, excuse me, something is taking a lot of memory on my computer and I don't know what it is. Let's have a look. H-stop. Ah, it's always Haskell language server. Let's just kill it. No, we don't want to restart it right now. It's clearly having issues. Alright, so first thing we're going to do is I'm going to take the buffer in as an argument. The buffer we're trying to create memory for. We're going to get the buffer memory requirements of that buffer. We're going to find an appropriate memory type. So we'll have to write this function. So given the memory type bits of the mem requirements, and we'll probably need the physical device. Pass that in. And the properties required for the memory. We'll get a type index. Then we'll just go back into the normal sorts of things that we do, which is resource.allocate. And then we'll give it instructions on how to allocate the memory and how to free the memory. Great. Oh, I've indented that wrong. Okay, this vkmem structure is our Vulkan input. Right. Cool. Now this find memory type function. This is just from the Vulkan tutorial, so I'll just copy that in. And we'll go through it. So, why am I doing that twice? We're getting the device memory properties of the physical device. We are going through giving an index to each of the memory types that we have available to us. And then we're seeing if that type is suitable given the properties that we've asked for. And if it is, we add it to a list. And then we just choose the first element of that list. So, pretty simple. We'll just import what we need to import. We've got this binary AND here, and binary shift. Device needs to be an argument to this function. Need to import lift.io. Then we can give this a type signature. There we go. We've gotten some memory for the buffer. Now let's call that. Okay, physical device context. Need the vk device from the context. We need the buffer, the staging buffer. And then we need the properties. So here's where we can specify the properties. So we want this memory to be host visible. So the CPU is the host. Or you can think of it like that. So it needs to be host visible to us that we can transfer data to it. And also we want it to be like host coherent, which I'm not sure I can explain very well. But essentially it's just like good for us to write to and read from, or maybe just write to. So that gives us buffer memory that is good for us to write to. Maybe not optimal for the GPU to read from, but that's okay because that's the stage. This is the staging buffer. We'll bind the buffer memory to the buffer, and then what we're going to do is grab the pointer for that buffer. So we're going to grab a pointer, and that is just a raw Vulkan call map memory. We need to give it the device, the memory itself, staging buffer mem. We need to give it an offset. VK create and play video game function should compile the next C that opens Skyrim 2. I wish. I wish. It's a somewhat inconsistent interface though. It seems like a very high level. So this map memory, device memory, offset, device size, and flags. So device memory, this is the offset, this is the size, vertex buffer size plus index buffer size. And then honestly, I've been a bit disappointed with Bethesda for a while. I didn't vibe with Skyrim as much as I vibed with Oblivion, and everything else since then's been pretty bad. So I'm like, well, it's not bad, I just don't really vibe with it. It's not my favorite. So we've got a pointer. We're going to cast the pointer to the right type. I'm going to put a bunch of vertices in it, and then yeah, I heard bad things about Starfield. We'll cast, what we'll do is we'll cast the float pointer to a word 16 pointer, which is the type of the indices. But first we're going to advance the pointer, the vertex pointer, the length of vertices. So we've poked a bunch of vertices there, but that doesn't actually like advance the pointer, at least not from our perspective. We need to manually advance it, cast the pointer to word 16, and then we'll poke our indices. So now we've uploaded our data to the staging buffer. Let's do this again, but for the final device buffer. Call this device buffer and device buffer mem. So this is the same size, same usage. It's a vertex buffer, it's an index buffer, but instead of being a transfer source, it's a transfer destination. Again, it's exclusive. We're not sharing it between queues. The memory is, we want to get appropriate memory for the device buffer. In this case, it's not going to be host coherent or host visible. It's just going to be device local. Device buffer mem. Then we'll bind the buffer memory, just like before. Device buffer mem. Great. And now we need to copy the buffer. Oh, yeah, I know. My voice is going to be so sore after this. Too much talking. Okay, copying the buffer. So what we're going to do is we're going to take this staging buffer and we're going to um, copy it to the device buffer. And that's how we can upload data to the GPU without getting a pointer to the device buffer um, explicitly. So copy buffer. Let's write that function. So we're certainly going to need the device. We're going to need a command pool to acquire a command buffer from. Um, we're going to submit a queue to submit the command buffer to. Going to need the size of the buffer, and then we're going to need the two buffers. So buffer source and buffer depth. All right. So just like we've done before, going to allocate a command buffer. In this case, just one. So we're just going to copy this from our draw code. Excuse me. Um, we're going to grab that one buffer because this allocates multiple command buffers, or it allocates them in the list. We just need one of them, so we'll just grab the first element in the list. We'll begin the command buffer. We'll add the appropriate end command buffer call as well. And then we'll submit just like we do in draw. So we submit a command buffer. We're not going to have any semaphores or wait semaphores or signal semaphores. All we're going to do is we're going to submit and then just wait for the device to be idle, or the queue to be idle. So let's have a look at this function. Queue wait idle. Yeah. So this is equivalent to having submitted a valid fence to every previously executed queue submission command, then waiting for all those fences. So just waiting for the command to be done. When you wrap up, you'll work on your EOTE. Is that the elemental, the Temple of Evil or something? What does EOTE stand for? Edge of the Empire. Oh, that's cool. I really like tabletop RPGs. So might have heard of people playing that. Is it like a recent thing? Is it like the D6 system? Oh, not at all. I don't know, I feel like there are a few Star Wars TTRPGs. But okay, dice pool system, that's cool. Yeah, there's this what's it called? Dungeon Masters Toolkit. There's this podcast called Dungeon Masters Toolkit, and this guy really likes his Star Wars RPGs. Tiered success and failure, that's cool. Yeah, okay. Oh wait, hang on. Gotta do this here. So in between begin command buffer and end command buffer, we're going to copy a region of a buffer. So that's this command copy buffer. We give it a command buffer, source buffer, so buffer source, buffer destination, and then we're going to give it the region to copy. And with that, we'll wait for the queue to be idle, and we should have copied the buffer. So we'll give this a type signature. And we should run this. Maybe. Should we? Yeah. So what we're gonna do is we're just gonna like this VK command buffer is it creates a resource, and we want that resource really only to exist for the lifetime of this computation, so of this block. So we're just gonna run that resource. That way the command buffer only exists for as long as it really needs to. That'll make this IO, I think. Okay. Oh, I've got a better. Here we go. All right. Cool, and that'll copy the buffer for us. So let's do that. Copy buffer, get the device out of the context, the command pool, got that hanging around. The queue, I'll come back to that. The size, so vertex buffer size plus index buffer size. The source buffer, which is the staging buffer. The destination buffer, which is the device buffer. And that's it. So, right, source, that queue. Oh, yeah, we can just get that out of the context. BK graphics queue. So at the moment we have two queues, a graphics queue and a presentation queue. We can submit this kind of operation to the graphics queue. So we'll just use that. And we're only going to do this once. Anyway, it's just a once-off operation. So let's see if that compiles. Oh, we should probably add this example to our cabal file if we want it to get compiled. All right. Looks like we might have some things to import. Here we go. So we start our import journey. to get these resources. All right. 66. IO. Cool. So we have uploaded the data to the GPU, so that's great, but we can't draw yet. And the reason for that is we're going to need to bind our vertex buffers and our index buffer in the draw kind of loop. We're going to need to change the pipeline to accept a vertex input structure. So whereabouts is that vertex input? Yep. So the pipeline has a vertex input state create info structure. At the moment, these two fields are empty, and that describes our vertex data. So we're going to need to have some way of modifying that. But once we address those two things, we should be good to render our square. So what we're going to do is we're going to change our subpass info structure. We're going to add some more information to it. So we're going to ask it for the vertex attributes and the vertex bindings. So if we look up this vertex input structure in our documentation system, we should see, yep, so it's got these two, the first two arguments are like, we're not going to use them. The only two arguments we care about are these two, which is the vertex input binding description and the attribute description. So we'll open those up. And that's why we're just going to take these two as arguments. We'll make them a list instead of a vector, because that's just a little bit more convenient for us. Put a VK in front of it. All right. Great. So that way, in here, we can pass that information in. Vertex bindings from the subpass info and subpass info vertex attributes from the subpass info. And we'll have to convert it to a vector. Great. And when we create the subpass info, which we do much earlier on, I'm going to need to add these. So what do these look like? Subpass info. Alright, that looks something like this. So this is... So we're going to need to describe three things. The binding is the binding number that the structure describes. So like when you bind the vertex buffers, the order in which you bind them, it matters. And so like the first one you bind is going to be binding 0, and that's what this is like referring to. So what you're saying here is like, I'm referring to binding 0, the first thing I bound. The stride is the stride between consecutive elements within the buffer. So in our case, that's going to be like 5 floats, because we've got 3 floats that are 2 floats that are position, 3 floats that are color, that adds up to 5 floats, and so the stride is going to be 5 times the size of a float. And then the input rate is whether we're like, it's a vertex input rate or an instance input rate. The rate at which vertex attributes are pulled from the buffer. So we've got first vertex buffer bound. The size is 5 times the size of a float, and we're just going to have a vertex input rate. So good to go there. And then the attributes, we've got 2 attributes, position and color. So let's have a look at the attributes. So the input attribute is the location, the binding, the format, and the offset. So the location refers to the shader. We see you've got this location here. Got location 0, which is the position, location 1, which is the color. So BK vertex input attribute description location. So here we're referring to the position. The binding, in this case, they're both going to be 0 because we're only binding one vertex buffer, so it's just the first vertex buffer bound. The format, we're going to just give it the format of 2 floats. We have to specify a color format, which is a little bit interesting, but this will do. Because, yep, so our vertices are made up of 2 floats for position and 3 floats for color. So this format kind of matches that. And then this will describe the color. So the location is 1. The binding is 0. We're only binding one vertex buffer. And then the format will be 3 floats. RGB S float. And this is the offset. Should mention that. Oh, nice. Yeah, getting the right name is difficult. Like, I just wanted Sam BNT, but I couldn't do that. So, cool. So the offset of this second attribute, the color, is 2 floats, because the first 2 floats are for the position. Float times 2. Not too bad. Alright, so we've described our vertex inputs. Now we need to describe the buffer and the buffers we're calling. Or the buffers we want to bind. So I reckon what we'll do here is we'll create a new data structure. Just put it up here. Call it draw. So draw is going to have a draw call. It's going to have vertex buffers, so a list of vertex buffers to bind. Yeah, that's annoying. Okay, so when we bind the vertex buffer, we actually kind of need a buffer and the offset in that buffer. So let's make another type for that. Data buffer ref equals buffer ref buffer. Cool. Definitely made a spelling mistake there. So this way the draw code will know what buffers it needs to bind. Because at the moment it has no idea. And when it binds a buffer, there's like an offset. So, because like the indices are going to be kind of offset in the same buffer as the vertices. And something that we also need to know for the indices is the index type. We'll just kind of like hack this in here. That's basically just the size of the indices. All right, and draw call we'll get back to. So we're going to add this draw structure, so subpass info draw to the subpass. So each subpass is going to have a draw, or possibly a list of draws, but right now we only need one. Cool. So let's subpass info. Cool, we need to add the draw here. Info draw equals draw. We've got the draw call, which at the moment we're just going to leave as a unit. Draw vertex buffers. So we're going to we're going to bind one vertex buffer, and that is the device buffer. And the offset is 0 because the vertex is right at the start of the vertex of the buffer. And the draw index buffer, again, we've just got one buffer. It's also the device buffer, but it's offset vertex buffer size. So the indices are after the vertices, and we've got to specify the type, index type uint16, because that corresponds to the word 16 type of the indices. Okay. Cool. And so let's go back to our draw code. So when we're going through the subpasses of our render pass, oh, wait a sec. We're going to need to pass this draw info on to the next stage. So subpass draw. And we'll just give it the same type. So now when we're creating our frame data, rather than just giving the pipeline, we're also going to get the draw out of our subpass info structure. Well, hang on, let me see if that's going to work. Let's have a look at my notes. What did I do here? All right. Let's change this. So we're going to work in the resource monad, get the pipelines, and we'll just zip the render pass info subpasses. It's a little bit screwy, but it'll work. So we're just going to associate the subpass info with the pipeline that we've made. And then with that, so we've got a subpass info, we've got the pipeline, and then we're going to create a subpass out of that. Subpass, it's just going to be made up of the pipeline. So you can see in this type, it's made up of the pipeline of the draw. Subpass info draw, subpass info. So my instincts are right, I just was missing some implementation details. Cool, so we've passed on the draw information. Now, when we go to, that was making the frame data, then we go to actually draw that frame data. And we're working on the subpasses here. We bound the pipeline. Now we're going to have a look at our vertex buffers. So for each vertex buffer in the draw vertex buffers in pipeline now has a draw. Sorry, the subpass now has a draw. That's going to give us a buffer ref with a buff and an offset. This is a vertex buffer. What we're going to do is we're going to call command bind vertex buffers. Give it a command, give it the command buffer. The first binding. So like we're going to bind a list of vertex buffers. So we can set what the first binding is considered to be. In this case, we're just going to set it to 0, which is kind of just what you'd expect. Oh, actually, we can bind multiple vertex buffers. So let's do that. So let's iterate over, given the vertex buffers, we'll iterate over them. And we've got the vertex buffer offset. We're going to output 2 separate lists. So in one list, we're going to put the vertex buffer, and the other list, we're going to put the offset. Because this is the format that Vulkan, like bind vertex buffers, expects. So let's pretend that worked. We've got vertex buffers. We'll just say like when not null, oh, we can actually just say unless the vertex, unless there's like no vertex buffers to bind, then do this. So let's look for this function. I think it's called like unzip. So yeah, like it's kind of what we want. This is going to give us two lists. One of the vertex buffs and one of the vertex offsets. And then I think that'll work. Or something like that. Let's have a look. Where am I getting issues? Okay. Five, 7, 1. Oh, here we go. 305. Just fixing some errors. I think this is some indentation issue. Nope. I'll have to have a look at that later. All right. So back to this. That looks like it's okay. It's not complaining. So let's do the same for the index buffers. What is that command? Command bind index buffer. We'll have a look at that. So we don't actually have one where we can bind multiple buffers. So we'll just do one at a time, which is fine by me. It's a little simpler anyway. For M. So for each of the draw index buffers in the draw, it'll give us a buffer ref of the index buffer, the offset, and also the index type. And all we're going to do is command bind index buffer. Command buffer, index buffer, offsets, and index type. Great. So we should have bound everything now. Bound our vertex buffers, bound our index buffers. Now this draw is wrong. What we want to do is an index draw. And what is our index draw going to be? Let's have a look at the parameters to that function. Draw indexed. Copy them over. So command buffer we've already got. We've got an index count. We've got, so draw index. We've got, let's write these out. Index count equals 6. Instance count equals 1. So we've got 6 indices. First index, that's 0. The vertex offset is 0. And the first instance is 0. So command buffer, index count, instance count, first index, vertex offset, first instance. Alright, that should do us. Cool, so now we just need to fix this type error, and then we'll be good to go. So what's going on here? That doesn't seem right. So where's our loop? What are we doing wrong here? Presenting. Minute.io. Minute resource. Minute.io. Minute.io. Reset fences. Just bear with me. Always fun to fix issues live on stream. I'm almost certain it's some kind of indentation issue. Yeah. Alright, well let's give this the type we think it should have. Here we go. That's not a monad. Nor is this. Zip. I think that should work. Well, it looks like it's working now. Let's actually test it. No, kind of. What happened there? I mean, okay. That looks like it's fine, just my windowing system was messed up there. Cool. So we're rendering a square to the screen using vertex buffers, which is exactly what we set out to do. All right, let me just have a look at this. Yes, definitely cat with cool glasses face. We got there. Sometimes it can be very exhausting. Okay, let's commit this code and we'll call it like working vertex and index buffer example. All right, I'm going to take a quick break and then we'll come back for the last like half an hour or so of the stream. And what we'll do when we get back is you'll notice that we copied all of this code from the triangle thing, and we're not actually sharing any code with the triangle thing. So even though we've changed this code, it's not being shared with the triangle. Like the triangle has like a very slight variation of this, which is not good. We should try and not repeat ourselves. So we'll fix that. We'll share what we can between the two, and you'll kind of see, I guess, the start of the rendering engine in what we share between the two. Although engine is a strong word. Cool. Take a quick break, and we'll be right back. Thanks to everyone that's been watching and staying for the stream. It's not always entertaining, um, but hopefully here for the journey. Cool. I'll see you guys in a little bit. Okay, we're back. Thanks for the follow I got during the break. Really appreciate it. Um, it's good to have everyone with me on this journey. It's definitely a journey. Um, so we got our square, our vertex buffers, rendering. Um, and what we're going to do is kind of share code between our triangle example and our vertex buffer example. So the first thing I'm going to do is fill out this draw call structure that we left as unit before. So let's define a draw call. We're going to have two kind of draw calls because we've got an index draw in the buffer example and a just like a normal draw in our triangle example. So we're going to need some way of distinguishing between those types of draws. So we'll start with an index draw, or it can be I'll call it a primitive draw, for lack of a better word. So let's define a draw call indexed. That's going to be like what we just did then. Going to have a index count, a instance count, a first index, a vertex offset, and a first instance. And we'll make sure to import what we need to import. With 32, int 32, and we'll just go ahead and do the same thing for a draw call primitive. So what's a draw call primitive? Get our first vertex, word 32. Got our first instance. Got our instance count. We've got our vertex count. Great. So in our draw code, well, let's start with our subpass. So when we're defining our subpass, we'll define the draw call. The draw call will be a index draw for this example. And the index draw is draw call indexed. We've got index count, which is 6. Instance count, indexed instance count, which is 1. Our first index, which is 0. Our vertex offset, which is 0 again. And our first instance, which is 0. And this is what we're doing now. We're just like trying to like not abstract Vulkan at all, just like leave things kind of flexible. But you know, we might change this in future and make this a lot more convenient. But for now, I'm going to keep it very inconvenient, so that we can find the pain points quickly. Cool. So then we're going to look at the call in our draw code, we're going to look at the draw call, case draw call, draw of index draw. If it's an index draw, we've got a draw call indexed. And that's got index count, instance count, first index, vertex offset, and first instance. Cool, and then we just got the appropriate draw call. And the other draw call we could have is a primitive draw. Draw call primitive. Got first vertex, first instance, instance count, and vertex count. And let's steal that from our triangle example. Got our vertex count, instance count, first vertex, first instance. Great. Now our draw code is a little bit more generic. Let's pull that out. So let's pull this, everything up to end command buffer. I'm going to call this record frame data. So we've got a function called make frame data. Now we're going to make a function called record frame data. So command buffer and frame data. Now, will we need anything else? We'll probably need the swap chain, and that should be good. So like I said, we've got this make frame data function, which takes a kind of description of the render passes and creates frame data for each swap chain image. Let's make this record frame data. Just going to paste in our code that we copy pasted. It's going to command buffer, swap chain, and frame data. And most of this is going to be the same. Should almost all be the same. Oh. Should indent correctly. So this is going to take our description of the frame and we'll render to it. Let's see if that compiles. Yeah, looks good. Do we actually need swap chain? Yes. Add a signature. Bennett.io. Cool. All right, now this is the code that we're going to steal, that we're going to extract out and share between our examples. So let's create a new module, render/types. Let's get rid of the old module. We're not using that anymore. We'll copy these types over. Just everything from here to here. This is sort of our description for our render passes. We're gonna have to import some things, but we'll get around to that. And then let's create another module, just a top level render module. And it's kind of what we want. And we're going to cut out these two functions, make frame data and record frame data. And we'll share that between our examples. I'm not sure what's going on there, but probably nothing that important. We'll add these files to our cabal file. Add these modules to our cabal file. All right. Now we'll need to import all of this. Ah, what's going on here? Let's fix our compiler errors first. Import root.render.types subpass info render pass info. Great. We'll import with32. Import this. Import Vulkan. Okay, that's good. Need to use data kinds. And draw call indexed. Just importing things. Then we'll need to import raw.render. Make frame data are two functions. Record frame data. Cool. Now I can start fixing imports here. Monad unless. Sorry, my Haskell language server is broken in this file. Import buffer ref. Oh, looks like that started working. So we'll load our example again, our buffer example. Examples.buffer. I don't understand that. Why would they want to send their mail to your house? Surely they want their mail. Okay, so we've extracted some of the code out. So at the moment, what we're doing is we've got some like setup, and then we are setting up. We're describing what our render passes are going to look like. We're using the make frame data function, which is in this render module now, to make the frame data. We're acquiring an image index, indexing into that array of frame data with the image index, and then recording that frame data. So now we should be able to share that code with our triangle example. So we can get rid of all this drawing code. Call the same thing, record frame data, command buffer, swap chain, frame data. And we can also, we should already be making frame data, but the interface is slightly different now. So we should update that. Hmm. Here we go. Don't know what's going on with my Haskell language server at the moment. Stop being like this. There we go, we're back. Can get rid of the shared code now. All of this stuff can go. Subpass info. Let's update that. So now we need some more information like the vertex bindings, which in this case is an empty list because the triangle example, all the vertices were hard-coded. Same with the attributes. Now we need to specify the draw. Draw in this case is, got the draw call, get back to that. Draw vertex buffers. Again, we've got no vertex buffers, so that's easy. Draw index buffers. No index buffers. The call itself is a primitive. Draw call primitive. Draw call primitive. First vertex will be 0. First instance will be 0. Instance count will be 1. And the vertex count will be 3. So just drawing a triangle, so 3 vertices. Make sure to import what we need. Okay. It's looking good so far. Get rid of all those redundant imports now. We'll do the same in buffer. VK extents. VK image views and VK surface format can go. Same in buffer. These 3. Cool. Now let's load our triangle example. Yeah, I definitely am seeing the CPU spike with the, it's like not IntelliSense, it's like the Haskell language server LSP mode for Emacs. Um, it does that all the time. And it sucks. So we can still render our triangle, we can still resize the swap chain. Let's try our vertex buffer. So that's still good. Great. So now we're sharing a bunch of code between our examples. We've got a little bit of a way of describing our render passes. Again, we're not trying to abstract too much. We're just doing the simplest possible thing and then we're going to iterate on it later. And yeah, we're sharing a bunch of code between our examples. So I think next time we'll finish up the stream soon, but next time we'll maybe either have a look at uniform buffers or we'll have a look at like memory allocation, because that's something that's important. We might look at using like the Vulkan memory allocator, uh, so that um, we're not doing this, creating like four buffers for or two buffers for every single resource you want to make. It's not ideal. But yeah, we'll see what happens next stream. I'll do some planning, and I'll see you guys same time on Friday in 2 days. So I'll be uploading this stream to. Oh, let's not go to YouTube. YouTube at Sam Bennett _TV. So this is my YouTube channel at Sam Bennett _TV. You've got the previous streams here. I'll upload this stream here. You can follow me on here on Twitch or on YouTube. And you can follow the commits live on this repo, which is github.com/sambnt_rort, RORT. So yeah, it was great to stream. I love streaming. It's been great. Thanks for your patience. And yeah, thanks so much, Valian, for sticking around and chatting. It's awesome. It's great to have you and great to have someone to chat to. Yes, and let's hope you're not my one lone subscriber for long. Yeah, so great to hang out with you guys today. Have a good night, have a good day, and I'll see you in a couple of days. Um, I hope things get more and more exciting as we go. Awesome. Yeah, just one person high squad. It's good. Thanks so much. All right, see you guys.